In this example, we are going to introduce slope fields. And slope fields are based off of the notion from Calculus 1 that we know that the derivative, y prime, which is the same derivative that shows up in differential equations, gives us the slope of the tangent line on the graph of the solution at that point. So what we're going to do is we have some points. We're going to plug those points into the differential equation, and we're going to get the slope of the solution at that point. And when we do that at several points, we form a slope field or a direction field for that differential equation. And that field gives us the general kind of shape of all of the solutions and can help us visualize what the solution of the differential equation is. Now in example 5, we're only going to find the slope for 3 separate points. We're going to find the slope at the point -1, 1. We'll find the slope at the point 0, 1. And we will also find the slope at the point 1, 1. Now we're only working with 3 points, so that slope field is not going to give us much information, but later on in this lesson we will discuss how to generate a more significant slope field. So finding the slope at the point -1, 1, this is our x value and our y value. I'm going to plug them into the differential equation because remember, y prime, which is the derivative, is the slope of the tangent line. So it gives us the slope of the solution at a particular point. So when x is -1 and y is 1, y prime is equal to, I'm substituting in -1 for x and 1 for y, and I get out -2. I go to the point -1, 1 on the graph, and I'm going to sketch in a little line segment that has a slope of -2. And I'll say that looks like about that. Remember, negative slopes go in this direction and positive slopes go in this direction. That's a positive slope and this is a negative slope. Now let's go on to the point 0, 1. So at 0, 1, y prime is, I'm looking here, I'm replacing x with 0 and I'm replacing y with 1 to get a -1. So I get a -1, that's still a negative slope, but it's not as negative as -2. So I'm going to draw that line slightly less sloped. And then at 1, 1, y prime is equal to x minus y. That's 1 minus 1, which is 0. So at the point 1, 1, I'm going to draw in a little line segment with a slope of 0. So those 3 little line segments give us the slope field for this differential equation at those 3 points. In example 6, we are given 3 separate differential equations, and we're also given 3 different graphs of slope fields or direction fields, and it's our job to match the differential equation to the slope field. So when I look at these slope fields, I noted 2 things particularly stand out to me. For example, in the second one, every single point along the y-axis has a slope of 0. Those little horizontal line segments, I can easily identify those horizontal line segments as a slope of 0. So just to point out, like this line segment here in green, I can tell it has a positive slope, but I don't necessarily know if it's a slope of 2 or a slope of 1. It's not evidently clear. This pink line segment, I can also tell that it has a positive slope. I know that its positive slope is more positive than the green one because it's sloped at a greater angle. So for instance, this might have a slope of 2 and this might have a slope of 1, but I don't necessarily know that. I just know that they're both positive and that the pink one is greater than the green one. But when I look at these line segments here that I've boxed in blue, I definitely know that every single point on the y-axis has a slope of 0. So let's start with graph B. And what we can observe is the slope at any point along the y-axis is 0. And it may be helpful to note that the y-axis is the vertical line x is equal to 0. It's 0. So I'm looking for one of these differential equations where y prime, because remember the slope is y prime, where y prime is going to be equal to 0 if I plug in a point that's on the y-axis. Points on the y-axis have x equal to 0, and I want the slope to be 0, so that looks like that matches with the second equation. So graph B matches the equation B of y prime is equal to x. So just a quick example of how I'm getting that. Let's say that I were to choose this point right here that looks like the point 0, 1 on the graph of B. If I were going to plug that into the differential equation B, I would replace x with 0. I'm plugging in 0 for x. And I would have a slope of 0, which is why we see that horizontal line segment there on the graph of B. Notice that that does not work on the graph of C at the point 0, 1, and it also does not work on the graph of A at the point 0, 1, because in both of those graphs, the slope is not 0 at that, right? Those slopes are positive. This is a positive slope, and this is a positive slope. Now let's go on and make another observation in graph C, where in graph C we can see that the slope at any point along the x-axis is 0. First I'll just write that observation. And the x-axis is the horizontal line y is equal to 0, is 0. So I'm looking for a differential equation where the slope, which will be y prime, could also be written as dy dx, is always going to be equal to 0 when y is 0. And that matches equation C. Equation C has that y prime is equal to y, and y is always equal to 0 along the x-axis. Finally, let's go on to see graph A. Just by process of elimination, we know that it's going to be matched with equation A, but let's check that. So to check that, I'm going to choose a point, and I'm going to choose the point 1, negative 1. The point 1, negative 1 is right here. No, the point 1, negative 1 is right there. And I'm choosing that point because I can see that the slope of the graph at that point is equal to 0. I can see that horizontal line segment there at 1, negative 1, and so I know the slope is equal to 0. So at 1, negative 1, y prime is equal to 0. Also notice that that's the only graph that has that going on. So in graphs B and C, the slope is not equal to 0 at the point 1, negative 1. Even if we hadn't already matched those, we would still be able to use this point to help us figure out the graph of A. So let's check that that matches the differential equation. Given in part A, it is x plus y. I'm going to plug in the point 1, negative 1. If I evaluate the derivative at 1, negative 1, this just means plug in 1 for x and negative 1 for y, and we do get 0, which verifies that we should be seeing that horizontal line segment there at the point 1, negative 1 on the graph of A. In this example, we start off with a differential equation, and we want to sketch a slope field for this differential equation. And then once we have that slope field, we want to use it to approximate a sketch of the solution that passes through the point 1, 1. So I have a table set up for us, and in this table, we are going to plug in some x and y values so that we can get the value of the derivative from the differential equation. We'll use the differential equation to get the value of the derivative at those points. So for my x values, I'm going to use negative 2, negative 2, which I'll pair with the y values of negative 1 and 1. Then I'll use x values of negative 1, again with y values of negative 1 and 1. I want to see what's going on at the point 0, negative 1, and at the point 0, 1, at the point 1, negative 1, 1, 1, 2, negative 1, and 2, 1. So I have several x and y values set up in my table, and now I'm going to be plugging them into y prime in order to calculate the slope at those points. So when x is 2 and y is negative 1, y prime comes out to be negative 5, which means that at the point negative 2, negative 1, we have a slope of negative 5. That's quite steep, so I'm going to draw a segment in like that. At negative 2, 1, when we plug negative 2 in for x and 1 for y, we get out negative 3. So at the point -2, 1, I'm going to draw another negative line segment, but not as steep. When I plug in -1 and 1, we get out -3. So at the point -1, -1, I'll sketch in a slope of -3. And I will continue filling out this table and sketching in the slopes of these line segments. When I plug in x is 0 and y is 1, I get out a slope of 1. So at the point 0, 1, I'm now sketching in a positive line segment slope with the slope of 1. When x is 1 and y is -1, I also get out a positive 1. At 1, 1, I get out 3. So I'm again going to sketch a positive sloped line segment, but I'm going to make it a little bit steeper since the slope is 3 there. And then I have 2 more points that give me slopes of 3 and 5 at 2, -1 and 2, 1. So this is what the slope field looks like from just the points that we sketched. This is still not complete, right? Because there's points in here along the x-axis that I haven't sketched. There's points up here when y is equal to 2 that I haven't sketched. And it would be very tedious for us to continue this table just to get more slopes to form a full picture of what that slope field looks like. So I used Desmos to generate the slope field for that entire differential equation. Linked on Moodle, I have a link to the calculator in Desmos that will generate a slope field for you if you put in the differential equation. And I will show you that right now just to show you how I generated that. So you would come into Moodle at the top of the 6.1 section and you will just click here for a slope field generator. And then once you open that up, the only thing that you would need to do is you would need to type in what your dy dx is, what your y prime is. So our y prime is 2x plus y, so you would just come into this equation here and you would type 2x plus y, and it will generate a slope field for you. So I just took a screenshot of this slope field and pasted it in here so we have a more complete picture of what that looks like. We're being asked to sketch the solution that passes through the point 1, 1. So here's the point 1, 1. And how we do this is we kind of look at the slopes that are near this point and we try to stay parallel to them. So for example, just following the curve that I see in here, I see around 1, 1. The slopes are doing this kind of behavior. Then it starts to kind of level out in here. Notice this has slope 0 right there. So I'm just going to kind of follow this pattern here. The graph then seems to be curving up. So I'm going to curve up and just kind of follow this pattern there. It looks like we get this parabola shape for the solution of that differential equation that goes through the point 1, 1. And this is how you use a slope field to approximate a solution to a differential equation. You form a slope field, a pretty complete slope field. You want it to be relatively complete around the point that you're trying to find the solution to. And then once you have all those little line segments in there, you'll go in and you'll kind of try to stay parallel to those line segments and follow the pattern that you see to sketch that graph.